if you're modeling something in space, we know that there's extreme temperature gradients, and these are hard to simulate. And the reason why we do this obviously is because we sometimes need active control, right? We need heaters and radiators to bring the spacecraft and the subcomponents into operable ranges. And the current techniques sometimes are maybe too conservative and still have a lot of uncertainties, right? And where are the pain points? So the cost of simulation sometimes is prohibitive to do what you would like to do on board. So not a lot of modeling is happening on board in simulation. So you can imagine that if you have a system that's subject to these high gradients and you have a critical set of components, you'd like to be able to control that environment, right? And in order to control the environment, there's always an estimation piece there. Something like what I'm proposing here would fall into that estimator, which would be part of a larger control loop to control the critical components. In this case, the thermally critical components. If you're working on something else in a different control loop, the paradigm would still be the same. Okay, so how do we propose to use PIML, this hybrid technique, to help us do onboard thermal simulation? One of the pain points is how to actually generate a nodalization to represent a spacecraft. And as you can see, this really complicated model on the top right called DemiSat, which we made up for this problem, of course. The goal here is that, okay, if you assign this problem to a junior thermal engineer, and say, okay, give me a really accurate model, they might tend to over-nodalize the entire spacecraft, right? Let me crank up the nodal density to as much as I can visualize, and then that should take care of all gradients and so forth. And if that junior engineer keeps working in some institute for a long enough time, they'll learn, okay, maybe you don't need as many nodes in certain places, and you can save costs by maybe only having 2x2 nodes on the solar arrays, and maybe you need to focus all your nodes on the green component, which is the optical bench here in this spacecraft. But you wouldn't know how to do that cost savings unless you've had years of experience, right? So actually generating this thermal model of this mesh takes a lot of effort and knowledge. And what we're proposing here is to learn how to do that nodalization from a neural network, right? And so in that way, we can actually save time in the engineering design process, right? But what's also nice about that is we can actually do this more often than we would otherwise. So a senior engineer may only be able to look at a whole mission. And so I guess we all have different backgrounds here. When I say a mission, you might have many different orbits. You might have a lot of different thermal loads over different orbits. And a senior engineer might only have time to look at the average loads and say, okay, I'm going to give you a smaller mesh, yes, but I can only give you something that works most of the time. I can't sit here and create a new mesh for every single orbit, for every single loading environment, right? So that's, even an expert doesn't have enough time to sit and make a low density or a reduced order model for every specific loading scenario. Now we could do that with a machine learning model, right? We can tell it, okay, I'll give you this orbital load profile. Tell me the optimal mesh for this scenario. And you can go one step further and you can say every time point in a loading profile, what is the optimal mesh, right? And that's something that even if you had the expertise as a human, you wouldn't be able to do that just because of time constraints. Okay, let me see if I missed anything here. Yeah, and when you combine these two things together, right? If you don't have, like, why would you ever not do complete high fidelity physics, right? Why isn't that always the option? Well, sometimes you want to save computational cost. Sometimes you need rapid prototyping to happen during a design process. You don't really have time to do all that modeling. So let me talk about that in a couple of slides. But okay, so our overall objective, to keep this in the back of your minds, is to develop an ML-based adaptive nodalization scheme, which will help us to reduce costs while still maintaining the interpretability that you get out of a physics model. And then, like I said, we're going to compare this to a few different baselines to test whether we've done a good job or not. Okay, so let me step back for the next couple of slides and talk about this topic in general. And as I was alluding to earlier, if you look at this trade space of interpretability, your prediction accuracy, and computational cost, we all know where high fidelity physics models lie, right? You're going to get the most amount of accuracy. However, the computational costs are really high, right? And so this is where we hit that, the problem that I was mentioning in the opening slide is if you have a control loop, if you have that control loop happening in real time on board, you don't have the luxury of having a high fidelity physics model to run on board, right? For various reasons, compute limitations, you need to respond, and robotic systems, you need to respond in real time as well. Okay, so what do? Traditionally, we've made low fidelity physics models, right? Let's just say, okay, in this case, the high fidelity one refers to something that has really high nodal density of that demisat that I showed. A low fidelity model might just crank those down to, let's say, a 2x2 grid instead of 10x10, right? Now that's fantastic because it's still a physics model, so you know how to understand that. However, the prediction accuracy goes down dramatically, right? And it's not a very intelligent way, like I was mentioning earlier, you can't really adapt that to every single loading environment, right? So there's some natural limitations there. The other option is, okay, if you jump all the way into the other camp of data-driven modeling, you can get a lot of predictive accuracy. So a lot of people have built, just let's say, let's ignore the physics, even in a system where we do have understanding and we have equations, governing equations, let's say we ignore those, we can build a data-driven model. We can get a lot of accuracy. We can even do it very quickly, in fact. However, you lose interpretation, right? And you can't really ensure you're following any physics. So that can be very dangerous, right? So this has motivated people across different research communities in academia and industry to go after something in the middle, which is a hybrid PIML range. And what does this get you, right? So the whole sales pitch here is this, that you should still be able to get a highly accurate model. You need that. And you still want to save some computational costs, right? Otherwise, what's the point? However, you need one more ingredient, which pushes you into a lot of creative modeling efforts, is the interpretability, right? So you need to be able to understand what your model is telling you. That's
very quickly. Can you give just a definition for a node?
of a node?
For a node, yeah.
Okay, so in this application, what I'm talking about today is a finite difference grid.
So is it's a spatial difference between 2 points?
It's a lumped mass model,
Okay.
if you're familiar with those. Wikipedia.
We'll figure it out. Mesh.
Yeah. Yeah.
Okay.
Okay, so this middle ground, this promised land of hybrid modeling, a lot of people have gone after this from different approaches, right? So I just throw this here, I needed this slide here to kind of demonstrate there's many different ways to do this, right? So you have some data on one hand, and you have your classic physics equations on the other hand side. How do you combine those two? There's many different ways of doing this, right? You can think of this as like a two-instrument orchestra, right? Or you can think of this as cooking with two ingredients instead of one. Whatever analogy works best for you, but the idea is there's not just one way to bake the two together, right? And the other takeaway point I'd like to point out is that this is a very recent marriage of the two techniques, right? So just a few years ago, this PINN model came out, and I think I have a slide on that as well. This one. This was interesting because on the left-hand side of this architecture, you see what looks like a neural network. Indeed, it is, and it's just predicting a physical quantity like you would have in any purely data-driven model. However, the authors went one step further and said, okay, this quantity U that's shown in this graphic is a dependent variable of a differential equation system, which you do have some understanding of, right? So now when your data-driven model predicts this quantity, we can plug that into your differential equation and get a new constraint on what the quantity ought to be. And therefore, you can compute an error from that and train your weights on your neural network based on that error term as well, right? So in this way, you're holding the hand of the training process towards being more physically relevant.
For the data-driven model, is that normally neural net as well? It's just like simple, like without using the differential equations, or like what does that mean?
So in the world of purely data-driven modeling, there's less wrong answers, right? So you could just say, okay, I want to build a neural network with this many layers and this many nodes. Is that the optimal choice? Maybe not, but you'll still get an answer, right? And then you can train and you can try to optimize that. But usually the penalty of being wrong there isn't very high, right? You can adjust and you can say, okay, I picked too many layers, this took too long, let me just cut it in half. Whereas you can't really do that with a differential equation, right? You're like, oh, I don't like these terms, let me just throw them out. Well, that won't work. Okay. Okay, so hybrid PIML models, what does this mean? And if you go and pursue this as a topic in literature, since it's a new subject, you'll find many different ways of describing basically what it's taking a data-driven technique and some physical process and combining them together. What I'll point out is that if you're coming from a machine learning perspective, there's many different steps in the whole process. So when we say physics-informed machine learning, what do we mean? We mean injecting an understanding of the physics in any step of that machine learning process. This could happen in where your data is coming from. So you could just take data from a physical system, right, that obeys laws of physics and use that. You could inform your loss function to have actual physics constraints in it. And you could even have your optimization routine also take advantage of physics as well. So there are many ways to combine the two together. And another way of looking at it is you can have them in serial or you can have them in parallel. So you could have a data-driven model like injected after your physics equations, right? So maybe equations give you first order magnitude results, and then you have a machine learning there that goes on top, which does some error reduction, right? Or you could have them go in parallel, where you use the data-driven technique to maybe estimate some parameters in your physical system. So hopefully that gets some ideas going in your mind about how to do these different types of techniques. Here's one example of my co-authors. They worked on this problem to predict flight parameters of a VTOL craft using just the flight orientations and control parameters. And so the type of model that I'm going to be talking about today, as I speak 50 words a second here, is one that takes your original inputs and has a neural network right up front, right? So this is happening in serial, and it predicts components which go into a reduced physics model. That's the VLM model labeled here. It doesn't matter. It's a vortex lattice method, if that means anything to you. But the idea here is that you have a low fidelity physics model, you have a high fidelity physics model, but you can use data from the high fidelity simulations to predict input parameters for that low fidelity physics model. Okay, so let me explain that in a bit more detail. Perhaps too much detail, but so the parallel to the last graph here is that on the top left, where you have inputs and weights, those go into your neural network layers, and you're predicting transfer parameters. And so those are your input parameters to a reduced order model, right? Now, the key point here is that simplified physics model has to be differentiable. And so if you work in machine learning, you need your models to be differentiable so that you can learn from actual data by computing errors and then propagating the gradients back through your network, right? So the takeaway message here is that when we combine these two techniques together, we have a reduced order model, which is differentiable. And the second thing I want to point out here is the training data on the top right is that's coming from your high fidelity physics simulations. So the assumption is you have a high fidelity simulator that you can query, and you can run some simulations from that, but it's too expensive to use on board and practice, whether that's happening on ground or on board in a spacecraft. But you use that to train this hybrid model to create a model which is faster, because a simplified physics model is always going to be faster than a full fidelity physics model, right? It's still a physics model, so you can interpret its results. However, it's adaptive to scenarios, and I'll talk about that later. And with just a little bit more computational costs of running that neural network up top, you can get better performance than just a pure simplified physics model. Okay. So back to our example here, right? So this dummy satellite that we're simulating has a few different faces. And typically we would simulate this with software called Thermal Desktop. And that's all you need to know right now. Okay, so here's what happens typically to simulate a high fidelity simulation to get a thermal profile for a spacecraft. And I've highlighted here in red the two main pain points, right? From the perspective of simulation. The first one is the one in the middle left there, is that some engineering experts have to sit down and create a thermal mesh model, given your spacecraft, given your orbital loads, engineering design requirements. And like I said, okay, what if I give you like 10 different loading profiles, right? So even if you're working on terrestrial ground-based robotics, your system is not going to be subjected to just the same loads, right? Usually if you're building a robust enough system that you care to simulate, you're going to have a variety of loading environments. So this engineering team is tasked with making one nodal mesh, which answers the call for all those loading scenarios. And we know that's not really feasible, right? So that's what we're addressing here today. But I wanted to give the big picture here to say that that's not the only place, right? So when you're thinking about opportunities to infuse machine learning, I recommend zooming out as much as possible and really understanding from your engineering teams where the pain points are. Not some things are cooler to do, but some things are maybe more practical. The second pain point here, if someone does thermal modeling in this room, is computing radiation view factors. So that's a very intense calculation. We have ray tracing hardware these days to help do that, but we'll be studying that in the future. Okay, so this is your simplified physics model. So I'm going to talk about simplified physics model, how we use that in our PIML model, and the other baseline technique, which is your purely data-driven model. So this simplified physics model, it's simplified because we're just looking up some view factors instead of computing those radiation view factors I mentioned in the previous slide. And on the far left there, that finite difference grid box, the thing to note here is that's fixed, right? So you just have a grid and then you're able to compute the physics given that grid and the thermal loads. And in the end, you get a thermal profile, right? What this PIML architecture does is, if you now notice that finite difference grid is being created by the neural networks, right? So we're asking the neural network, here are the loads on a full fidelity simulation. So in this go around, right, the engineering team only has to compute the thermal loads on the high fidelity model once, right? And those are usually given to you, right? You could say, okay, well, that's extra work as well, but let's assume those are given to you. And now we're asking the model to give me a new mesh specific to that loading environment, right? So note the distinction between the paradigm and the last slide, where the engineering team only gets to pick one model, right? In practical terms. This time around, we can have a different nodalization for every single loading scenario. And to answer your question, oh yeah, you have a question, go ahead.
Well, sorry, yeah, I guess, so you mentioned that you're just given those loads, is that for like one point in the simulation or just across the whole?
So you have when I say loading profile, I mean a time series of loads. And since this is a finite difference grid, like I was mentioning to you earlier, you have loads for different points on the spacecraft over a certain amount of time. In this case, for one orbit and maybe multiple orbits. So it's spatiotemporal data. Right. And think of it this way, right? So if you could place your nodes on this model intelligently, you would be able to capture the thermal gradients better, right? Rather than just them being fixed. Where you put those nodes on a physics model matters, right? And so let me talk about what this well, let me say this, right? So the art is in designing which parameters you're learning with that neural network. For our scenario, since we're doing thermal modeling, as I motivated earlier, the pain point is that nodalization, right? For your applications, that might be a completely different parameter. However, in this case, we focus on learning the nodalization in that network And so then, once you know that, you can formulate that network as needed. In our case, it was just a 5-layer network, and it outputs the number of nodes on the spacecraft for each surface. So it's a dummy sat that I showed in the beginning. It's a CubeSat with some solar arrays and has 11 faces. So this neural network has 11 outputs.
Since the neural network is outputting for each surface, does that mean like if your satellite geometry changes, like you can still use this with different satellite?
But that's a good question. So, I mean, if it changes, so there's two types of changes that could happen. One, you could have an articulating component. And in that case, your thermal loads would change because your view factors would change, right? In that case, you should be able to include that in your training set, that variation. However, if it's a completely different satellite, then the answer is no, you would not be able to generalize. So you would have to do this again for a different spacecraft. Yep, good question. Okay, so we design, I'm gonna go a bit quick here, but we designed this neural network to tell us how many nodes to put on each face of the spacecraft, right, given the loads. And the second thing we can do, here's the, the art and the fun of it, is in the loss function, we can bake in different penalties, right, to guide our training process. So you see 3 terms here. The first one is the least controversial one. That's just your error term, right, which says, okay, you predicted a temperature at the end of the entire loop. How does this compare to the high fidelity physics? That's your primary error term. It's normalized in the denominator by the prediction error for 2 nodes that we fixed. So we said, okay, let's have a 2x2 grid and have a 4x4 grid. And we want our answer to be somewhere in between that for this example problem. In reality, your range might be a bit wider. The second term there is a computational cost. So you want to have accuracy, but you also want to maintain computational cost. Again, you can normalize that to ensure that you're not creating a mesh that's too big, right? Otherwise, it will take too long to run, and then there's no point in doing it. The last penalty ensures that you actually perform better than the lowest fidelity physics model. But aside from the details of this, I just want to point out a take-home message here is that if you go home and you've worked on physics and you worked on machine learning, I would encourage you to think about how to bake the two together. And the loss function, as I was saying earlier, is one of those places where you can do that. If you have physical constraints, if your system has conserved quantities, you can include them in loss functions as well. So there's definitely an art to doing this. This is the baseline model. It's just an artificial neural network. And I'm running low on time, so let me just keep going. Okay, so here are some results, and let me show our thought process behind why we did these comparisons. So the first row there is a fixed model that has 2x2 nodes across the entire spacecraft. So in that case, let's say a thermal engineer says, okay, too many orbits, just make a 2x2 grid and just use that. Next one is 4x4 nodes, right? So the engineer could say, okay, I feel kind of shaky. I want to have more nodes on here, so I'm just going to do 4x4 nodes throughout. By the high fidelity physics model in this case has 10x10 nodes. The third row there is a purely data-driven model. That's just a neural network that has the same density as your high fidelity physics model, and it just predicts the temperature at the next time step, given your first loads, right? So I skipped over the details there, but that's all that it does. That last model, the PIML model, is the entire architecture that I talked about today. So you'll see here that I spent the most time talking about PIML, but the ANN performed really well, right? So the root mean square error for the ANN actually is pretty good. It's better than the physics models, and its runtime is better than all of them as well. So that's very interesting. And you'd scratch your head there a little bit. However, the reasons why we don't just do data-driven modeling, right? This was a small dummy example, right? And so you can, in a very small simulation, you might get results like this, but there's still some downsides because the ANN, as in the purely data-driven technique, cannot extrapolate. For instance, if I've given it thermal loads for a specific orbit, it might not be able to tell me the performance for an orbit which has loads that it hasn't seen before, right? Secondly, if you look at the comparison on this side, the red line here is the data-driven model. Because there's no physics baked in, it's not going to perform in a manner that's physically plausible, right? So you have this behavior where it's really accurate at earlier time points, this is one orbit, and later time points, but in the middle, it looks like, that's probably not physically possible given the loads here. This was a thermal profile for one of the nodes. Okay. So same thing here. This is just looking at one of the faces at one time point. You can see the comparison between the PIML on the top left. It predicted only 2 nodes, right? And therefore it's less accurate than the ANN, which has as many nodes as the high fidelity physics model. Okay, so there's many challenges here, right? First of all, you have to have an auto differentiable model. You're supposed, downscaling and upscaling is an issue as well. And for PIML architectures, everything is problem dependent, right? So that transfer network that I mentioned, it depends on your specific problem. There's a lot of art and science to combining the two techniques, but it is very fruitful. This initial work that we did is promising, even if those error metrics are not fantastic for this simulation. When we crank up the number of orbits we're feeding in, this was only 6 orbits. We expect to see some bigger gaps there. And there's many other things we could do, right? You could ask the network to not only tell me the density of nodes there, you could also ask it to tell you where to put those nodes, right? So in this plot here, for instance, we asked her to tell us the density in this panel, and PIML said 2, so we just put 1 node in the bottom left, 1 node in the top right. But if we also allowed the network to tell us where to put those nodes, we might have gotten better results, right? So there's many things you can do here, and if there's a takeaway message here is that I definitely encourage you guys to think about and this is an opportunity to be creative. I think if you come from the traditional field of doing physics, usually there aren't as many opportunities to be creative. Maybe that's controversial to say, but certainly when you combine the two, there's opportunities to do something new, and I really encourage you guys to explore that. Thank you.